We'll get started in 1 minute. Hey, good afternoon. It's time for us to start. So first, I requested a larger classroom, but I haven't gotten any response yet. So if we do change classrooms at some point, I'm gonna send you an email with that information. But for now, we're still here. And then in our previous lecture, we were discussing the flow systems within a facility. And also we started discussing the departmental planning or product family departments. And the last thing that we discussed was the direct clustering algorithm methodology for planning cells within a department. And we went through the steps of the DCA algorithm or the methodology. They're listed in this slide. And we also discussed this example number 1. So at the end of the lecture, I asked you to go and review this because we have a lab today. So we're gonna spend some time working on a different problem. So before we get into that, let's just review this example. So again, we are trying to use this matrix that is representing per machine. At the top, we have 5 machines. And based on the different part numbers, we know we have information about which parts needs to be processed by each machine. So for example, you look at the first column. In that column, we have the part numbers. Part 1 is processed by machine 1 and 3. Part 2 is processed by machine 1 and so on. So the idea with this direct clustering algorithm is to try to come up with a way to split these groups so we can form different manufacturing cells. So we can focus our processes based on the type of part that you need to process. And we can design a separate cell for those group of parts that require the same type of machines. So in this case, we started with this information. And the steps of the algorithm are the following. You start by adding totals for each row and the totals for each column. So those totals are represented in green. So for the first row, we have a 2 as a total. Second row, the total is 1. Third row, the total is 3, and so on. And then the total per column, you have 3, 2, 2, and 2. From there, we start the sorting of these rows and columns. So we start by looking at each column, and we try to we start by looking at each row, and then based on the before we get into sorting the columns, we need to sort the totals for the rows and the columns, and that's what we have here. So we are going to sort them, the rows in a descending order. So we start with 3, and then the rest of them are 2 and 1. The ties are broke using the part number. So if you have 3 2s, like in this case, you're going to put first the highest part number, then the next one. So that's what we did here. We sorted them in descending order. And then for the columns, we sort them in ascending order. We start with the 2s and then with the 3. And the same thing, we break the ties based on the machine number. So 5, 4, 3, and 2 in this case. After we perform the sorting, then we start looking at the movement of the columns and the rows. So we're going to start with each row, and we're going to see if there's an opportunity for us to move one of those columns to the left, so we can group the ones as close as possible. So we look at the first row, which is highlighted here in yellow. The first column has a 1, the second column has a 1, the third column is empty, and then we have a 1 here. So we can move column 2 toward the left. And then the rest is going to be empty. Once you move a column to the left, those columns are fixed. So for example, column 5 is fixed, 4 is fixed. When you move 2, it's also fixed. So if you perform any other movement after this one, you don't move the ones that you already fixed. So in this particular case, once you move to so in terms of the columns, once you perform the first row, you move to the next one. You see that these two are together. So there's no need for you to move 5 and 2. Those 5 and 4, they're already fixed. 2 is already fixed. So we move to the third row. You have a 1, but you cannot move that to the left because this 2 is already fixed. So that basically completes the movement of the columns. And then once you have completed the movement of the columns, you look now at shifting rows up. And we go through the same process. We start with columns now, and we check if we can move ones up. In this case, those ones are already up. In this case, you have both of them already up all the way. And then you get to this column number 2, and you see that you have a 1 here. That one can move up. You can move that up. So that means that this row can be moved to in between rows and 6 and 4. And after that, the rest of them are okay. So this is going to be the final matrix after you have performed those sorting and also the shifting of the columns and the shifting of the rows. Then once we get to this point, we have to see whether or not we have an opportunity to split these parts by machines. So we can group some of these machines to focus on specific parts. For this case, the answer is yes. We can split this into 2 separate cells in which we're going to have parts 3, 6, and 5 being processed by machine 5, 4, and 2. That could be a separate cell. And then you can have a separate cell with machines 3 and 1. and they're going to be processing parts 4, 1, and 2. Any questions on this? We also look at the second example. In here, I'm not going through the overall process and just showing you the initial matrix, the initial information. And I'm giving you the final result, which is what you see on the at the bottom of the slide. The reason I'm doing it is because I want to illustrate a point, right? So right now I'm not focusing on the methodology. I'm focusing on the final result, in which we're trying to split this into separate cells. And in this case, we notice that there's no clear cut between the number of parts or the type of parts and the type of machines. What we notice is if we cut and we try to create a cell for machines 2, 3, and 1, there's a part in the other cell that is going to need machine number 2. Same thing if we split it in machines 2, 4, and 2, 5, 4, and 2 as a separate cell. We notice that for this other cell, we're going to still need machine number 2. So that's something that can happen, and we have possible ways to solve that problems. We have two ways in which we can solve that problem. The first solution is to place that machine that is needed by both cells in the middle, like I'm showing here, and then build the other cells around that machine. So in this case, you have 2 in the middle. You can have, let's say, 5 and 4. And then here you have machines 3 and machine 1. Right, and then both cells are sharing that machine. The other option you have is to duplicate or basically purchase a second machine. So you can have one of those machines in one cell and the other machine in the other cell. But it's going to be the same type of machine. And then you can completely separate both of the cells. So that's what I'm illustrating here. And I think that was the last thing we did. Yes, sir.
So is the parts and having them in 2 separate cells not an option at all, versus buying a whole other machine, just splitting up the parts? For example, part number 5, I would have some at machine 2 and some at machine 3, versus buying a whole machine, just putting the parts in different places.
So what you mean is, but the problem is that, if I'm understanding what you're saying correctly, the problem is that part type 5 needs to be processed by both machines. So if you separate this part type from the cells, from any of the cells, you have to make sure that that part is processed by these 2 machines.
Okay. I was some component, not that it's finished. Okay.
Yeah. So it needs to go through both machines in order to be completed. Okay. Good question. Any other question? Good. So what I want you to try to do now is to attempt to work on this problem. See if you can get a solution. I'll give you like 5 minutes, maybe a little more. You can just take a piece of paper. If you're not comfortable, if you don't understand completely the algorithm, try your best, okay? Just want you to have questions. Like if you don't try, you're not gonna have questions. So try your best. If you have questions, let me know. We're gonna discuss the problem and the solution in class. So it's not that you're gonna lose points or anything like that, but I need you to try at least. So you can see where you're stuck, and if you can clarify that before leaving the classroom, that would be great. If you have completed step one, this is how the matrix should look like if you follow the steps. You do the summation per row, summation per column, and then you order the rows top to bottom in descending order. For the ties, you put the largest part number first, and then order the columns in ascending order from left to right. And the ties, you break them, putting the largest number for the machine first, and then the rest of it. Here, you're talking about this. So all of the rows, top to bottom in descending order. So we look at each row and we are gonna sort them in descending order. Okay. Here? That one? Yes. 32211.
Yeah, the second two. Has like one.
Okay, so okay, so I see what you're saying. So let me. Better?
So I understand that right now, the three has one, on one, two, one, on four.
3 has one here and one here. And 2 and
Oh, sorry, part number one.
part number 1.
Yeah.
Okay. Has one in 1, 1 in 2, and 1 in 5. This is 5, this is 2. So it's the same. Here you have for machine 1, you have part types 1, 2, and 5. Here you have 1, 5, and 2. And that's after sorting them. That's why the rows are in different order. I mean, if you're still confused, you can come here and tell me exactly what's going on. So on this step 2, I just copy the same matrix. It's the same matrix. Just want to have a different figure to manipulate now. So in step 2, we're going to look at each row, and we're going to see if we can move elements towards the left. Right, so we are going to start by looking at this row, and we're going to see if we can move columns toward the left, so we can start grouping these ones towards the left. So if you look at the first element, it already has a 1. So we don't do anything there. Then this one is empty. And then we have a 1 here. So that means that we can move that column toward the left. So 2 can be moved here. Same thing, 1 can be moved next to the 2. And that will be for the first row. So the matrix now look like this. It'll be scene number. You have 4. You have 2. You have 1, and then 3. And since you move already, you fix 4, you move 2, 2 is fixed, you move 1, 1 is fixed, you know 3 is gonna stay there. So you're done with the shifting of the columns. So this is gonna look like this. Part number 1, 5, 2, 4, and 3. And that will be the end of step 2. We move column 2 toward the left. Part 4, I mean, we start with 4. We look at the first row. 4 has a 1, so 4 is fixed. We look at 3, there's no 1 there. Look at 2, column number 2, there's a 1, so we can move that in front of 3. We look at the next column, which was 1. There's a 1, so we can move it after 2. I'm sorry. Yes, after 2. So it's going to be 4, 2, 1, and 3. Then we have to look at each column to see if we can move rows up. That will be step 3. So I'm going to do the same thing. I'm going to use a different color. It's going to be a step 3. And I'm going to copy this same matrix. I'm going to write it in blue. Sheet number This is 4, 2, 1, 3. Part number 1, 5, 2, 4, 3. One. So now instead of looking at each row, we're going to start looking at each column. I'm going to look at this column. I'm going to see whether or not I have opportunities to move rows towards the top. So you start by looking at this. There's a 1 there, so you don't have to do anything with that one. This is empty, 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 and then you have a 1. So 3 can be moved after 1. Okay, so new matrix. Let me 4, 2, 1, 3. And then the part number will be 1, 3, 5, 2, 4. So this is 1, 1, 1, 1. Okay, so I'm done with the first column. Column 1. Oh, here in 2. Okay, good. Yes, thank you. So that'll be here, right? Thank you. So now I have to check on the next column, this one, and see if there's any opportunity for me to move once up. So there's this one, right? But I already fixed 1 and 3, so there's nothing I can do at that point. So that makes 5 also fixed. Then I look at this one. Any opportunities? Yes, 2. But then 1, 3, and 5 is already fixed, so they will stay there. And then the only column, the only row that haven't been touched is 4, but the other 4 are already fixed. So at that point, I'm done. Yes. No, because you go column, you start with this column, right? This first column, and then you go row by row. Since you have 1, the first or row one has a one already, that automatically fixes that row in that position. That's a good question. So once you check that, if you have one there, that's fixed. Any other movement that you do is not impacting that row. Good question. So now we got into this final matrix. So step 4 is try to come up with a separation of, see if we have a clear separation of cells. The answer is no. So we have we're facing similar problem than the one that we face in this example. So the answer or the final recommendation will be based on which one of the alternatives you want to use. If you want to share one of the machines, you have to identify which one you're going to share. In this case, pretty clear, you have a conflict. Use a different color. So if you try to split this like this, and then like this, you know, this machine one is going to be needed by both cells. So you can design a cell that will be sharing that machine. So for instance, in this case, that will be 4 and 2. And then this one will be 3. Or you can have you can buy another machine one and split the cells. So you have 1, 1 and 1, and 3. And then 4 and 2 separate cells. Well, the important thing is that you're able to identify where the conflict is. Okay, so that in this case, that will be machine one. So in your solution for the lab, you can decide, okay, I'll go with this design, establish that as your solution, or the other one. As long as you present one of the two, then you should get the full credit. But remember, one gives you more flexibility, or it's more expensive, right? You have to purchase another machine, but you have more flexibility in terms of where to place these machines and how to set up the layout. If you go with a single machine, then you're more constrained. You know that machine one has to be shared, has to be in the middle of both of the cells. So you have less flexibility in terms of the layout. Questions?
I have a question actually.
Yes, go ahead.
In step 1, when you're organizing the rows in descending order,
Yes.
part 5 and 2 have the same value and part 4 and 3 have the same value. So then how do you know which one to put first?
So the question is, when you have a tie in the total for step 1, how do you decide which one goes first? So the tie is based on so if you're looking at the rows, then you're looking at the part number. So for example, part number 5 and part number 2 have the same total, which is 2. You put 5 first because 5 is the highest number. So it's just a rule. Doesn't make that it's gonna, I mean, as long as you're consistent you should get the same solution. But the way we are breaking the tie is by looking at the part number value and choosing to put first the highest one. Same thing for the machines.
That makes sense for this application, but then what does that part number mean? Because
Part number is just an ID. But again, this is just a rule. You can go the other way around. You can say, okay, I'm gonna put the lowest first. And then as long as you're consistent, you'll get the same answer.
yeah, because if you do put the lowest first, you get more defined cells, and you don't have to share a machine. But I guess it would depend on what those parts are.
Well, if you want, we can discuss this offline because I cannot hear you very well. So if you want to join my office hours, we can talk more about it.
Okay, that's fine.
Good. Sorry for that. So let's continue. Any questions here in the classroom? Good. Let's continue our discussion. So go back to combining what we discussed in our lecture last time and what we completed discussing today. So we look at material flow systems and also layout types. So we are now trying to put those two together. And I have some figures, some illustrations here that shows the flow and how is that impacted by the type of layout. So the type of material flow system is determined by the makeup of the activities or planning departments among which materials flow. So as noted previously, there are 4 types of production planning departments, and those are listed here: the production line departments, the fixed material location departments, product family departments, and then the process focus departments. So 4 types of production planning departments. We also illustrated when would be best to use any of this. Remember that a figure which you have low variability in volume, high variability in volume, and then based on those 2 parameters, you decide which one will be a better fit. So that's part of the slides that we covered last time. Sorry, so if you need more time, let me know. So these are the 4 types of production planning departments. And then we go one by one, stating the advantages and limitations. So we start with the production line product layout. So here we have at the top a figure that illustrates that layout. So you see you have different type of machines located in series. Each one of these machine or lines are focusing on specific product. So if you have product 1, has to go through all these steps. You have a production line that's going to have all those 4 steps, and you put that product through that line. You see that there's a couple of drills in this one, drills. So you have a drill in each one of these production lines, but they're located after different operations. So the sequence in terms of the product is different. You go from getting the material into each one of these production lines, depending on the product, final assembly, and then into the warehouse. In terms of product layout, advantages, logical, right? You know, you have product one goes through this line. It's gonna follow that sequence. Product 2 will go through this line. Product 3 is gonna go through this line. And so on. So when I work for Johnson & Johnson, and that's typical, you have different type of, let's say, Tylenol products, and you have so if you're looking at Tylenol for kids, there's a production line that is going to be focusing on the ingredients, how to mix them, and then how to package them, and so on. You're looking at there's like 100 different type of Tylenols. So you have a specific production line that is focusing on this each type of products. Smart working process inventory should result. Again, you're keeping the ingredients that are needed for that specific product. Total production time per unit is short, material handling requirements are reduced, less skill is required for the personnel. So those are some of the advantages, the limitations. This is a very big one. We've observed that a lot. If you have a problem with that line, and that's the only line that is producing that product, if something happens to any of the machines, production stops. It's not going to be able to produce that product until you fix that problem. So that's a limitation. Product design changes cause the layout to become obsolete. So if you're coming with, let's say, a different way of mixing the ingredients, faster way to mix the ingredients, you might need to redesign the whole thing to accommodate that new machine or that new process. Slowest station paces the line. So that's based on the bottleneck rate. So if you have a slow machine in that line, that bottleneck is the one that is going to dictate your production. So it's not like you have space to, I mean, you might, but if you have a production line, most likely you have a station focusing on that specific process, single machine type of production process. So capacity for expansion or adding a second machine might be limited. So that's why the slowest station faces the line. General supervision is required, and high equipment investment usually results. So as I mentioned, you have multiple drills and you need one for each one of the production lines. So that requires additional investment since you're not sharing those machines. And then we get into the fixed product layout. So things like, again, boat you want to put together, or an airplane. So you have the product in the middle and everything is going to come into that area. So that's what we're trying to illustrate here. Everything's happening in here. Some of the advantages for the fixed product layout, material movement is reduced. When a team approach is used, continuity of operations and responsibility results. Everybody is paying attention of what you're doing with the product. You completed this task, so we can do the next one, and so on. Provide job enrichment opportunities. So people, again, are learning from, I mean, waiting for you to complete this. Can I get involved, or and so on. Promotes pride and quality because an individual can complete the whole job. High flexible can accommodate changes in product design, product mix, and product volume. Limitation, personal equipment movement is increased, may result in duplicate equipment, requires greater skills for personnel, requires general supervision, may result in increased pace and greater working process, and requires close control and coordination in scheduling production. So again, if you're waiting, let's say you're looking at a house, building a house, for instance, you need to wait for the walls to be completed for you to go inside the house and try to continue with the process. So that's the type of environment that you are working in with a fixed product layout. Say that again? Yes, same thing, because it takes a longer period of time. These are usually customized type of products that take longer and more expensive, yes. Fixed product layout, product family layout. So now, I have mentioned this example multiple times. So cell phones, you have multiple products, but most of the actual product can be sharing some of the components or most of the components. So you have a product family, and you have all these areas in which you have a product route, and they will go into the areas that are needed to be based on the product route in order to be completed. So some of the products will go through this station, and then maybe skip this one and then move to the other one, and so on. Or we'll just go straight to one of the stations and then move on. So in this case, for example, one product will go through this process and then go out. Some of them will go through these three and then go into this area and then move out. So it will depend on the differences, but there's some shared properties. And that's what this product family layout is trying to optimize. So we have all these area stations, we establish the route of the product, and then we take the product according to that route. Advantages by grouping products, higher machine utilization can result, right? So you're trying to make the best use of the equipment that you have available. And since these products have changed some of the parts, sub-assemblies, and so on, you can take advantage of that. Smoother flow lines and shorter travel distances are expected than for process layout. Team atmosphere and job enlargement benefit often result. Again, there's many products that are being produced in the same area, so you get to learn about the different products. Have some of the benefits of product layouts and process layouts. So it's a combination trying to take most of the benefits from both and exploit that. It is a compromise between the two. Encourage consideration of general purpose equipment. Limitations, general supervision is required. I think this is overall for all of them. There's a need for supervision. Greater labor skill required for team members to be skilled on all operations. Production balancing, control balancing is very important to make sure that you're putting the right working process, the right amount, so you don't create all these big queues in the manufacturing area. If flow is not balanced in each cell, buffers and working process storage are required in each cell to eliminate the need for added material handling. And there's a final one is decrease the opportunity to use of the special purpose equipment. And then finally, we have the process layout. So you have now areas that have the specific amount of machines that are the same. See here, there's an area with all these machines that are the same, another area with all the machines that are the same, painting, welding, mills, assembly. So it's very process oriented, and that's the name. That's where the name comes from. And then depending on the type of process that you're gonna need, you're gonna bring that product to that station, complete that operation, and then move to the next area. This increases machine utilization. General purpose equipment can be used. Highly flexible on allocating personnel and equipment. Diversity of tasks for personnel and specialized supervision is possible. So if you're you're an expert on these milling processing, then you can focus on that. Limitations, increased material handling requirements. So again, if you have a product that requires all these operations, then you have to have a way to move that product across all these areas. So material handling requirements are pretty high. More complicated production control required, increased working process. Let's say you have a batch of 100 units, all of them needs to be drilled. You take these 100 units and you wait for all of them to be completed. That increases the working process. Longer production lines, higher skills required to accommodate diversity of tasks required. So very good summary about these different process, different type of material flow systems according to the layout. And that will be the last slide of this lecture. I think we still have time, so I'll get started with the next topic. I want to make sure that there's no questions. So, is there any questions so far? The last, the one that we completed today. Yeah, you have to upload the solution by midnight. So, but you upload that on Canvas. Okay. So let's get into the next part, and we'll see how far we can go before we stop the lecture. So let me open the slides. So this is a continuation of the lecture that we just completed. Let's see. And here we're going to focus on these two items, activity relationships and space requirements. So the idea is that we are going to start quantifying the flow, and we'll see how that can be useful in terms of planning our designs, like quantifying how many units are being moved from one area to the other. The idea is typically want to have a unit that is common among all the items that we are moving around the facility, so we can compare them based on that base unit. So we'll see how that connects with our discussion. So we want to understand the interactions between flow system, flow activity relationships, and space requirements as they relate to facilities planning. So activity relationships, again, these are ways of understanding the flow. So we can quantify it. It could be quantitative, it could be qualitative. But what we want to gather is information about what's happening between the areas and what type of flow is happening between certain areas of the facility. So these activity relationships, measuring the activities among departments, is one of the most important elements in the layout of departments. So we need to understand the flow between the areas. Why? Well, as we discussed already, material handling equipment tends to be very expensive. So if we don't plan according to the amount of flow that we have within the facility, we might end up putting a lot of money or putting a lot of resources in buying material handling equipment. That if we plan ahead, if we understand, let's say there are two areas that have a lot of communication or had a lot of flow, we can plan to have them as close as possible. So we limit the amount of material handling that is needed to move the entities between those two stations. And that's what I'm trying to illustrate here. So here there's a figure showing different departments. These are process-oriented departments. You can see that these two, foundry and late, there's flow happening between them. They're kind of far from each other. Same thing here. So if this color representing a high volume flow, then you see that there might be a problem because you have a lot of interaction between these two and they're kind of far from each other. So we want to understand, want to have a way to quantify the amount of flow that is happening between these areas. To evaluate alternative arrangements, activity relationship must be established. Activity relationships may be specified in a quantitative or qualitative manner. Yes.
So there's no activity between like
Foundry and drills looks like there's some foundry and welding probably.
there wasn't that green.
If this was not there, that means that there's no activity. Yes. So the arrows are representing that connection between and flow between the areas. Yes, that's right. So that's why you see office by itself, since it's not part of the manufacturing process, not receiving anything from the other areas. So there's no necessary flow between drilling machines and the office. So that's good. But you still need an area to have management or for human resources and so on within the facility. That has to be planned. Yeah, good question. Good question. So one thing that is very important is that these can be specified quantitative in a quantitative way or in a qualitative way. So if you don't have maybe the numbers, you have a way to gather that information. Maybe this is a new facility and you don't have a way to measure because flow haven't started yet. But you can gather some information, some type of qualitative information, and we can use that to attempt to plan for this. So for example, a chart can be used in flow measurement is the mileage chart. This is looking not necessarily from the point of view of designing the internal facility or the inside of the facility, but for example, if you're trying to plan for the location of a new warehouse, this could be useful. So you have a way to quantify the flow in terms of mileage. So you have a from to chart here. This is from to, and then you have an understanding. So if you go from Atlanta to Boston, mileage from Atlanta to Chicago, Dallas, and so on. So again, gives you an idea. So for example, if you look at this first row, San Francisco is way, like on the other side of the United States. If you look at from the Atlanta perspective, you would expect to have that high number there. And it looks like from the perspective, I'm just looking at these numbers. San Francisco is the one that is creating the largest distance from the other cities. So you can see that after designing this type of chart. So if you notice that, then you can start looking at options in terms of trying to reduce that mileage that you're gonna have obvious mileage that's gonna happen if you decide to locate far from San Francisco. So that's a tool. When distances between two cities are symmetric, the mileage can be represented in a triangular mileage chart, which is maybe easier to examine and to understand. Right here, you have all the cities again, simple numbers, and the way you interpret this, you have this city and this Dallas, the mileage between Atlanta and Dallas. So you look at the intersection, and that will be the number. If you look at let's say Pittsburgh and Boston, you go here, here, and this is gonna be the mileage. A very simple graph, but very useful. Quantitative flow measurements. Flow may be measured quantitatively in terms of the amount moved between departments. So now we're going back into the inside of the facility. The chart most often used to record this flow is a from to chart. So that's what we are presenting here. So it's the same idea, right, here from the mileage chart, but now we're looking at the flow between the departments inside the area. And this is under the assumption that you're moving the same item, right? So so if you can see here from stores to miling is 12, miling to plate 7, turning to plate also 4, assembly to warehouse 7, and so on. So same idea. Now we're looking into the inside of the facility. We are trying to quantify, maybe this is a daily flow. So how many times you're moving things from one department to the other. Based on these numbers, this is the highest number, followed by this one. So this can tell you like, okay, so these two are experiencing this very high flow. So we might be interested in putting those areas close to each other when we are designing our new facility. Some of them have no interaction. Those empty spaces, meaning that there's no flow happening between these two departments of areas. So we might not need to put them. They can be far away as they need to, because there's no flow. Okay, so here's some steps for constructing this type of chart. So we're gonna start by listing all departments down the row and across column following the overall flow pattern. And then we establish a measure of flow for the facility that accurately indicates equivalent flow volumes. And this is what I was referring to. You have to have a common unit of measurement. Like if you're moving boxes and then you have like a pallet, you cannot say, okay, I'm moving one unit if you're moving a pallet and moving one unit if I'm moving a box, because they're different in size, the amount of units and parts that have contained, and so on. So we have to have a unit that is common among the things that you're moving through the facility. So if the items moved are equivalent with respect to ease of movement, number of trips may be recorded in the front two chart. If the item moves vary in size, weight, value, shape, and so on, then some common unit of measure may be established so that the quantities recorded in the front two chart represent the proper relationships. Based on the flow paths for the items to be moved and the established measure of flow, record the flows of volumes in the front two chart. Okay, so I don't think I'm gonna have enough time to complete this. So I'll stop now and we will continue from here. Yes, sir.
I have a question. Considering these flows, consideration there, defects or loss. In your original chart for the part, the initial source to milling was, so when you look on the tube for milling, it only accounts for 9 of the 12 pieces.
When, yes, so from here to here is
You got 12 pieces.
12.
But when you look at from milling, how much output is from milling?
Oh.
Other areas, there's only 9.
There's 9. Okay, I see what you're saying. So
Want to do a 1-for-1, or do you need to take into account for prospective loss of defect?
that's a good point. And what I can tell you right now is that we are not taking into account defects right now. This information right here is not accounting for that. But if we are trying to balance this out, I don't think that's the purpose of this chart as we are illustrating it here right now, but I understand what you're trying to say. Good point. Any other question? No questions, good. So I'm gonna stop here. We're gonna continue on Monday. Remember to upload your lab. Easy, 20 points. Do it now. Don't wait until night and you forget. So do it now. Take a picture, upload the file to Canvas, and then I'll see you on Monday. You too, sir. Yes.
This is just actually my first class of the semester. I just registered on Saturday,
Okay,
this Saturday, and
so I have recorded every lecture so far. So if you have access to Canvas, you can go to the modules and everything is listed.
I'm also subscribed to your YouTube channel.
Okay,
So I
great.
was watching.
So the question is, send me the assignments that are already closed. You can submit them via email. Just send me an email.
The only one I haven't done is yesterday's, the one due today, sorry, by 12:30. I did everything else. The one due to by 12:30, I haven't done that
Okay,
one.
so yes, if you complete that one, just send it to me via email.
All right, thank you,
Okay,
sir.
no problem. Yes, sir.
I
Yeah.
So
Yeah.
when I was asking you, my main point was about this, okay? I did it before you even started class. I was doing it. Okay. So hopefully I won't forget now. After we changed, okay, I understand now.
This
we're
is
gonna-
step one,
we
right?
This is step one.
Mhm.
When I went to step, quickly,
So you're trying to
Should you
sort
go
this,
to-
right? First, you sort this.
yeah,
in
I
descending.
also, like, I have a way of
Mhm.
sorting this. Then after you sorted this, I just did 3, 2, 1, 1, right?
Yes.
My problem was here. Then what did I do? According to this, I moved these, right? So I
Mhm.
looked at 3, sorry. Uh, my-
So the rows
Okay.
are moving up and down, right? So in order for you
So,
to get
yeah,
this.
so three stays. Three
Three
stays
stays,
as a 1.
and then this guy 5 is moving all the
Then,
way
then
up.
what I did, I have 5. Since, here's my problem, since there's 2,
Mhm.
I moved 5 first. That
Yeah.
belongs to the first 2. And then the second, this is the first 2.
Yes,
I was looking at 2. Why did I move 5? Because it's larger, right?
yes, yeah.
Okay, and then for the second 2, which is 2,
You put 2 there.
2.
Mhm.
And then for 1, 1, since we use the largest one, we
Yes,
have 3 and
4
4.
and 3.
I was using 4.
Yeah.
Here, my problem was when you removed, then this was 1. And then I had 1 on 2, which is I moved 1 on 2, and 1 on 4, which is I have it, 4, 3, 1 on 1, 1 on 2, and 1 on 4, 1 on 1. My problem was this one.
Five.
Looked at this one, 1 was on 1, 1 was on 2. 1 was on 1,
1 is here.
sorry. 1 was in 1, 1 was in 2.
Mhm.
Okay, that's it, this was my problem.
Okay. You got it? Yes. Yes, sir.
So I spoke to you on Monday about I was originally scheduled for the same day and then reopened for the following day.
Mhm.
I viewed it the same day. Or I viewed it the following day, it was closed,
Yes.
and then I got a notification later that it was reopened
Mhm.
the following day. So I just emailed it to you,
Okay.
so I don't have to be able to accept that.
Yes, yes,
Okay.
I'll take it. But from now on, we're gonna make the due dates the same day at midnight. So for example, today,
I submitted this one on Monday. because it was
Okay.
this next-
okay, yes, that was my bad, but from now on, it was previously scheduled for Monday. Since we didn't have time, I moved it to Wednesday. So yes, so but for now, every time we have a lab, it's gonna be due same day at midnight. Okay? Yes.
So let's say you had a part that could be manufactured on 2 different machines, it could be manufactured on machine 1 or machine 2, would you treat it separately? You would treat it as machine 1 on this
If
side?
that's the case, I mean, let's say you have a part that can have, it could be manufactured, I mean, the process that you need can be done in any machine. That will give you more flexibility. And
Like,
then,
if you were doing the substructure, would you treat it as this instance, I'll treat it as it's only being able to be manufactured on machine 1. This one I'll treat
oh,
it
for
as
the
it's-
final solution,
yeah.
yes. So I will treat it as, I mean, if you are able to split it into 2 cells, then I would try to allocate that part to one of the cells.
Right, but I mean, for the determination of it, would you just treat it as like your initial diagram?
Not working.
So let's say part 1 on machine 1, machine 2, or machine 3. So would you just treat it as part 1, this one? Oh, okay, got it. So part 2, so you say like this,
Yeah, so this, because that's different. You have to generate a separate matrix to accommodate every single case.
so you do 3 matrices.
3 matrices and then solve and then choose the one that accommodates better your layout.
Okay. And then,
Because right now the matrix is showing all the process
that are needed. Right. For each part. Okay. And then I guess also the determination of whether you purchase another machine or put the machine on the boundary of the system. Obviously, the demand for the parts being manufactured on the machine exceeds the production capacity of the machine. You buy two machines.
Yeah, so if that machine becomes your bottleneck, then that will put major weight into adding a second machine. Because if it is the bottleneck, that's the machine that is dictating the whole process speed. But if you have a machine that is rather fast and is able to accommodate, I mean, the capacity is able to accommodate both flows, and is not becoming your bottleneck for any of the cells, then you should be able to manage. Yeah. Mhm. No, I asked that question to the director yesterday, and even him didn't know what were the plans for the university. I assume, and this is my opinion, that we're gonna be closed tomorrow. That's my opinion. I got a message. I live in Kyle. So I got a message from the city saying that we should expect a winter storm starting at 3 a.m. Yeah. No. That's the safest thing to do. I would. No. Stay home. And if you send an email to any of the instructors, they should be able to understand. Like, you're not gonna risk yourself for a class. Yeah. Yeah, but I'm confident that they're gonna cancel in class. I mean, in person. Maybe you have a Zoom class or anything like that. But even that, you don't know with power outages and all those things. Yeah. Mhm.
So I'm curious to see.
Oh, so you're part of that team. Okay, so good that can I ask you a couple of questions about that project? So you guys want to do a simulation, right?
I don't think that's the. So I have senior design prior to this.
Yes.
And we had Dr. Jenner, and we were talking about simulation. Our main goal is to show traffic flow. So our metric that we're hoping to base the project on is safety. So what we're thinking now, instead of 3D simulation of traffic flows, we have a 4-instance safety incident. Into a truck travel and your safety incident. Then after like increase in to accommodate the weight of the truck, so then you reduce these safety incidents.
Yeah, so that's why I got a feel from Dr. Monta about this project. And my recommendation in terms of which software package to use would be to use Xenium. But then I started thinking about the actual goal of the project, and based on what she said in the email, it was you're trying to show that you can reduce the number of meters, right? So yeah,
Building
so when I think about a simulation model as a tool to make decisions, I need to know a lot about what is the uncertainty in the system. And what are the things that you cannot predict? Maybe some type of probability model. Like, is it, I don't know, is it that it takes this much time to drive through that area?
Yeah, like arena and basing everything off of the different distributions and then
Yeah.
determining like the accumulation of traffic, I think the simulation would be beneficial for that, but for ours, we were just looking at doing like a 3D model. Just
Yes,
kind of
and
seeing-
you wanted to show the, and it is doable.
show
you know?
like turning radius.
Yes.
But then a simulation would be at what point you start the turn, start here, and it gives you different turns.
So for me, it's like, you will be, I mean, you be better for the company to understand where the amount of risk that they're putting their employees every time they try to do that now.
Right.
You can measure that risk, and then you can also suggest, you know, if you do X, Y, Z, you can improve that radio. It's gonna cost you this much, but then the risk of you getting these accidents is reduced. And then, I don't know if you can get this type of information, but how much it costing them to repair or to, free an employee based on an accident. So you can put that into perspective. So it's gonna cost you this much, but at the same time, you're saving an employee or you are saving this much money by doing this.
Yeah.
I think that would be more beneficial than trying to build a simulation, because I think you can show whatever you want with the simulation.
Right. No, the simulation came as a result of the senior design phase, or a focus around how we would report out the success of our project, or what metrics are we basing the project around. Whenever we said we were basing the project around the safety incidences, it has been suggested that, okay, well, how are you gonna actually, nothing's actually gonna be put into place in practice. How are you gonna say whether or not what you're suggesting will happen in plan? And so simulation was a suggestion, but like I said, I think we can just show pretty clearly that you're not gonna have the safety incidences based on the facility.
If you can come up with some type of flow chart, flow diagram. And then you have all these steps. And then you can tell me, okay, there's some level of uncertainty here. I don't know what's gonna happen, uncertainty here. There's uncertainty in the arrival process. There's uncertainty here. If you have something like this, in which you have multiple areas where there's a risk associated, and you need to quantify that with a probability model. If that's the case, then you can certainly next move forward and start to you have build the probability model here, probability model here, probability model here, probability model here. So now you have all these unknowns, and if you try to solve this mathematically, it's just impossible. Because you need to have information. But if this is something that you can quantify with a number, then deterministic, and this is deterministic, you know that you're gonna get 10 sums a day, that's not gonna change. Then you can build something simple. You don't have to go through the simulation process. But the painful part of the simulation is this.
Yeah.
Building the model is not difficult. The difficulty is to extract the effective.
I think, even just talking through, I think what we determined was, like I showed you, those points of incidences, we'll just use that, and these are our areas of focus, and these are the causes of those incidences, and this is what we went out and to this action to mitigate those issues with like those.
Can you, for example, say, like in this area, there's this many interactions happening every day, and out of those interactions, 5 are incidents.
That's what I was thinking, it was like, if we had, here's your facility layout, this is your starting point. This is your, areas. Incidents that come caused by turning, car turning. So if you can eliminate number of turns. Okay. Reduce safety incidents by 30%.
Okay. But you can, do you have that data? That's the question. Do you know how many incidents are caused by?
That's what we're, so we reached out and we're waiting back if they're actually gonna give us any records of their safety incidents.
Yes.
So
Because
that's what I need first.
that's what you need first, and then based on the data that you have, you can say, okay, I have all these uncertainties. And then you'll.
But like I said, I don't even think we're gonna go forward with building one.
Okay, got it.
I think mainly we're just gonna,
But it could be something like a Excel spreadsheet in which you build, you can search for this Monte Carlo simulation. It doesn't require you to build a city or arena.
right,
You just have a spreadsheet and you quantify the risk for incidents, and then you have a probability model that tells you incidents are following the explanation. This is the P equals. So you have that explanation, and then you can just build that equation into the Excel spreadsheet. And that has to be connected the number of the arrivals happening. So if you change the number of arrivals, you throw down that equation, it will tell you what is the thing. If you have 100 people coming or 100 people come to the system every day, maybe this thing will take this will not. Then you can build a plot. This is how the number of cases are changing based on the number of arrivals that you want to see. And if you do this, what we are suggesting, we take contact. And then that will see the impact. You will show the impact.
I doubt they're gonna have any.
Yeah, I know. So that's why when we say simulation,
So I think we're, like, even I think we're probably gonna, I doubt they'll even have record. of the facility.
yeah.
I think they'll just say something got damaged. I won't actually be able to pinpoint where.
Yeah, unless they have a research-oriented person in their facility,
Yeah.
they're not gonna have that
So I
information.
think we're probably gonna deal mostly with anecdotal evidence. This is where we have. We plot that on our CAD drawing. And we'll make moves to mitigate that area.
Okay,
And I'm assuming that's how it's gonna play out.
got it. Okay, so now to get ready for my next lecture, I'm teaching here. Next
Are you
class,
staying this
yeah,
way?
I'm staying here. So
Did you say we were getting another room or no?
I'm still waiting. If I get a different room at some point, I'll send it. Yeah, good afternoon.